Okay, so the next series of videos is going to be on Unit 4, which is exponential functions and logarithmic functions. Exponential functions are something that we've learned in grade 11. Okay, now logarithmic functions, that stuff is new, all right? So this unit encompasses chapter 6 and chapter 7. And what I'm going to do in this video is I'm going to review this guy, get into some of the inverses of exponential functions, and that's going to lead to this guy. All right, so let's start off with the warm-up. What I have is a function in blue. Now this, I don't know, it looks like a check mark. Okay, it doesn't look like it's going on forever because there's no arrows on either ends. And what I want to do is I just want to answer all these mini questions about the blue function. Okay, so let's start off. I might want to put some, I don't know, some major points on the graph to kind of help me out, just to visualize. And I'm just going to answer the first one. So state the domain. The domain, we're going to be looking at the x values, and the leftmost x value looks like -4, and it goes all the way to the rightmost x value, which is 3. So I'm just going to write it like this. X belongs to all real numbers such that x is going to be between -4 and 3. Now we have to add in those little lines because we need to include the -4 and the 3. Okay, now the range. It looks like the lowest dot right here starts off at -1 and goes all the way to the highest dot at a height of 4. So I'm going to say y belongs to all real numbers such that y is between -1 and 4. And again, we're going to put those equal signs at the bottom of the less than signs because we want to include that -1 and that 4 as well. Okay, so the C is asking us to graph the inverse. There's a couple of different ways that you can do this. Okay, so first of all, what is the inverse? The inverse is taking this blue guy and flipping it over the y equals x line. That's what an inverse is. Okay, so you got to flip the blue line over the dotted line. Now you can do this visually, which is what I usually do. I just say, okay, well, this looks like if I flip it over, it should be diagonal, like right there. Okay, this one's new dot should be diagonal right there. And then this guy, well, that's a little bit tougher. I'm going to go one diagonal and half a diagonal. So then I'm going to go half a diagonal and then one full diagonal, and it's going to be right there. And then this one might be, let's see, 1, 2, 3.5 diagonals. So half, 1, 2, 3, and the new point ends up right there. Okay, so I just do it visually, but I mean, there's another way, and what you can do is you can take the actual coordinate of one of the points and you can invert it. So that's why it's called an inverse. All you do is you take your x and your y and you switch them. So you get 3 and -4, so this new dot is going to be at 3 and -4, which is right there. So you could always take all the other coordinates and just switch their x and y values, and you will get each of the green dots. Join them all together and you see you get kind of like a reverse of that blue graph. Okay, so we kind of write a -1 to signify that this is the inverse of the original function. Now we can answer those last two questions. Okay, so the domain and the range. The domain looks like it's starting at -1 all the way to the rightmost dot, which is at 4. So I'm going to write it like that. And then the range, let's see, the lowest dot is at -4's height all the way to the highest, which is at 3. So we got that guy right there. Okay, so very quick, just a quick warm up on inverses. Now let's talk a little bit more about exponential functions. All right, now this is an application type of question, and it's going to get us to kind of see what an exponential function kind of looks like. All right, so modeling Canada's national debt. The table below shows how Canada's national debt has been growing since 1990. Since 1995, the Canadian government has taken steps to slow the growth of the national debt. Complete the table below. So you have your independent variable, which is your time, and then your dependent variable, which is the debt in billions. Okay, so the first difference is you're just going to take the bottom number minus the top, bottom number minus the top, and so on. Okay, so I did the first one for you. 420 minus 400 equals to $20 billion. Okay, and I'm just going to complete the table. Now, if these guys were all the same number, I would know that it was a linear function because that would mean that this number would add a certain amount to get to this one. Then you'd add that same amount to get to the next one, and it would be just a y equals mx plus b type of equation. But since they're not all the same, you know it's not linear. Okay, so what I'm going to do is I'm going to look at the second differences. I'm going to take the bottom minus the top, and I get $1 billion. Again, bottom minus the top, okay, 1.05. So notice that these guys are not the same, which means it is not a quadratic function. All right, if they were all the same, it would be a quadratic function, leading me to think that this could be, it could be a cubic function, it could be a quartic function, but I kind of hinted that it was an exponential function. So how did we know that? Exponential functions grow with a ratio. Okay, so what I mean by that is if I take this number and I multiply a certain number, I should get to this one. If I take that and multiply it by that same ratio, I should get to the next one. That's how an exponential function works. Okay, so let's just try to do, the ratio. We got to figure out that ratio. So take the 420 divided by the previous one, and you're going to get that ratio. And if I do that for all of them, I actually get the same ratio. So since all these guys are the same, I can then conclude that it is an exponential function. Okay, so is the relationship linear, quadratic, or exponential? I already said that. It's exponential. Okay, so I showed you the work. Determine the function that represents the national debt, where T represents the years after 1990. Okay, so normally an exponential function looks like this. Okay, where you have some sort of a vertical stretch or compression. You have your original base and then your exponent. Okay, so your original amount is going to be your vertical stretch or compression. Okay, so in this case, it's a vertical stretch by a factor of 400, and that is because you have your original amount of debt. Now, this blue number is your base. Okay, so we're just going to go right here. All right, 1.05, that means your debt is increasing by 5% each year. Okay, and that's how it's getting to that $420 the next year. T is going to represent your time, so that is your x exponent. Okay, and is the function increasing or decreasing over time? When we look back, all the numbers are growing, so your debt is obviously increasing. Okay, so there we go, right there. Now getting into that review again, this is what an exponential normally looks like, an exponential function that represents a growth. That is where your base is something higher than 1. Okay, so notice that you do have some sort of an asymptote because you have your graph getting closer and closer to 0. So the asymptote is right at y equals to 0. You have one dot that's consistent, which is this point right here, your y-intercept. That is 0, 1. Okay, that's on pretty much all of the graphs. All right, and this guy is increasing. Now, if you look at an exponential decay, it's going to be a little bit different. It's kind of backwards, where it goes from high and then it's going to go lower. But notice that, again, it gets closer and closer to that asymptote. So it also has an asymptote of y equals 0. There is a y-intercept of 0, 1, just like before. Okay, and this decay happens when this base number is between 0 and 1. So 0 0.5, 0 0.25, something like that, a 0 point something number. All right, so this is basically everything that I had said before. The domain, it can go on forever, but there is a limit in the range because of that asymptote right there. You don't have any x-intercepts because that asymptote's in the way. All right, now if we do an inverse of that function, all we do is we switch around the y and the x. So it looks something like this, and it's kind of weird looking, but if we decide to graph that, it's going to switch everything around. So notice that there is no horizontal asymptote, there's now a vertical asymptote right at x equals to 0. That y-intercept is now an x-intercept. And notice that the numbers have switched around. It's not 0, 1, it's 1, 0. So there is no y-intercept because we have that vertical asymptote. Okay, the domain is actually limited, whereas the range this time is infinite. Okay, so let's take a look at what this might look like. All right, so I have my exponential growth and my exponential decay. And if I do the inverse, which is flip it over that dotted line, it's going to look like the red graph. So notice that you have that vertical asymptote. So the red goes closer and closer to that asymptote but never touches. It has that x-intercept at 1, 0. Okay, the domain is limited to only this side of the graph, whereas the range looks like this guy's going to go higher and higher, this guy's going to go lower and lower, so the range is infinite. And that's the same for this one over here. So once we flip the blue graph over to become the red, then it has the same thing, vertical asymptote instead of horizontal. You have your x-intercept right there at 0, 1, and so on. Okay, so this is going to start leading into what a logarithmic function is.